library type things I felt were somewhat useful, I hope, for particularly you should have had experience in this vein before reaching a graduate class, but if you hadn't, I thought it was a good idea to force you to get into the library a bit, and I thought it was useful to give you directions such as you might either give yourself or an employer might give you on occasion. You usually won't have complete information, like the names of the two individuals I asked you to look up. I deliberately left off the, like James W. Wallace Jr., I left off the Jr. and the W, having made sure there wasn't anybody else that's likely to be confusing in a phenolic sense. I wanted you to become aware of the biographical type material, like American Men and Women these days of Science, previous editions, American Men of Science, and other such things. A number of you came across Who's Publishing in Science, or whatever the exact title is, and there are Who's and European researchers lists, so that these things in a good library are available and are awfully helpful. If you, as I often, well, not so often, but sometimes get called on to meet someone from somewhere else or introduce someone, you need to know some background, and this is a place to go. Or if you have heard of a certain researcher but don't really know what his mailing address is, well, the odds are pretty good that they'll be current enough that the address will be correct. Of course, if he moves real rapidly, you won't find him. The one with Margaret Cycle, I sort of psyched myself out a little bit on that. It turns out there are, in fact, and some of you will find comments on the paper saying that there was perhaps 6 papers in the period in question. What got me into the problem was that I wanted you to get to the 8th collective index for chemical abstracts, because it has the year section from 67 to 71. The reason I said 70 was I was trying to make sure that you wouldn't have to go on and look into later, because after all, if papers appear in chem abstracts, there's a lag of 6 months at least, and often a year, and used to be 2 or 3 years sometimes. So I cut this back so you wouldn't have to look into the later ones, but that caused me actually to make a mistake in the inclusion, because there were 2 papers out of the 6 that were in 1971, and in fact the one I had in mind that you would think that the enologist would be most interested was one of them. So that's my fault, and if you feel you were cut unduly there, why, see me and we'll give you back the half point or whatever, because most everybody got nearly full credit on the question. The one on the paper that Margaret wrote on Quercus rubra, which is red oak, we use white oak for barrels, but nevertheless Quercus rubra is red oak, and it is used for bungs, and is botanically rather closely related. So that would be the most nearly, most directly a paper of interest to the enologist. Of course, a number of our other papers are quite applicable, and even the one on the eucalyptus tannin would be a good one. The Ulmus thomasini is elm, and of course that's somewhat in the same family, so there is some reason an enologist might be interested in those things. So in terms of answering that question, what I wanted you to do was to go to the collective, what I thought was the simplest way to approach the problem was go to the 8th collective index and get a list of her publications, and remembering that the way that's listed, if she's first author, then it lists the titles of the paper and the chem abstracts reference, and then if she's not the first author, it says see also, and gives the name, 2 other names in her case, to look up. So having looked all those up then in the chem abstracts, you'd know the year of publication, and if you wanted to do it, the title and the details of the paper. Then having obtained that information, that answered part of the question. The other part had to do with among the papers she'd published, which was most cited in 1972, and that was a pretty dead giveaway, having told you about the Science Citation Index that I wanted to go to that. The only confusions I saw there is some people, or a few people, didn't quite grasp how that index works. It has two parts, a source index and a citation index. And in the source index, it would list, say, Margaret Cycle's paper, or papers published in 72. I believe there were none, as a matter of fact, but if she had, they would be so listed. On the other hand, in the citation index, it lists the people who have cited her other papers. And they have some problems because that's largely computer prepared, so that Margaret Cycle was listed as MK Cycle in part of the listing, and as Margaret K Cycle in the rest of it. So that you do need to cross-look and double-check. Not only that, they're a little out of date sometimes, or you may want to look in more than one issue if you have a practical problem. In my case, I limited you to the 72, and I picked a year that was old enough that the cumulative volumes had been prepared rather than the current, more fragmentary volumes that mean you'd have to look it up in several. So with some errors on my part, I guess maybe we illustrated the point regarding that. A few of you got I was very interested in the list of things that you suggested that we add to the course, and I will act on as many of them as I can. I think several of them will come out naturally anyhow, but there are a couple that won't unless I make an effort to include them, and I will do that. But in case something you listed or think of later that you'd like to have included, if I don't get to it or it appears I'm not going to, keep me nagged, and I will include everything that I know about whatever it is you'd like to know about. What else would I like to say? I think a few people got goofed up on the question about the cyclization in that they picked, say, for instance, the flavonoid type compound and then went into many, many variations of that. Did a beautiful job of elaborating the one, but then forgot that there were other methods of cyclization, and maybe that's a matter of phraseology of the question or something. Maybe it's partly my fault, but in any case, we did lose points for that reason. It was clear that some people didn't quite understand the isoprene synthesis, and there was enough of a hesitancy there that I'm pretty sure it's my fault. I guess I should say something about the isoprene rule, so-called. Isoprene is 2-methylbutadiene. I did intend to say this, but I didn't get it done before. So butadiene is obviously the 4-carbon with the 2 unsaturations, and then 2-methylbutadiene then is isoprene. And the isoprene rule as such basically says that anything built up by isoprene-like units it is built of 5 carbon units, and the 5 carbon units is branched, so that one methyl is in a lateral position. Well, then that I think helps, and it turned out if most of you did it correctly, followed back with the acetate generation, you will find that the marked carbons were the ones surrounding the carbon on which the branch occurs. And then if you put 2 of those together, you end up with the thymol marked in the 6 positions that surround the 2 carbons that are central to 3 others. So most of you got it correct, but a few of you got lost in following the thing through from the notes. Well, I think those were the points that I wanted to bring up and make sure we were understanding each other. Anyone want to raise any questions from the class? Guess I'd better get my necklace on. Well, having heard nothing from the audience, well, we'll assume that the test is in history now. There were a couple of people that didn't do too well that I've asked to come see me, and you may wonder, what are we going to do with the grades? I would ordinarily expect to include the grade along with the second midterm and the final. I still intend to do that, but in the cases where the students didn't do too well, I'll be happy to consider some personal tutorial arrangement to make sure that the grade doesn't rise to haunt you in the latter part of the course. And anyone else that wants to come in and discuss any particular point will be glad to amplify it. We were just talking at the end of the period, and as usual at the ends of the period I seem to get into something that I'd like to have a little more time on. So I thought I'd come just for a second back to the question of how much tannin gets into wine. This chart was just a little bit too big to get on the paper, but it's hours up to 24, and that of course is 1 day, and then 2 days and on up to 200 days on the bottom scale, time scale, and you'll notice that's a log scale then. So that a log plot of the time versus the percent of the seed tannin extracted up to, of course, 100%, and we've extrapolated these lines up to 100%. The basis for the 100% was we took some of these grape seeds and extracted them exhaustively and then called that value the 100%. And the dots here on the 0% alcohol line are the actual experimental values, and then the rest of them are left off with the normalized line being used to show the extraction rate. And except for the 14% alcohol line, they're all pretty much, well, they radiate from a low value, but they're more or less parallel. What this suggests is there is a lag, that nothing much is extracted for an hour or so, and that would be reasonable, I suppose, in that the cells perhaps have to die, or at least the solution has to diffuse in and the material begin to diffuse out, so that you have a short lag apparently, and then from then on this scale it's a linear development of the extraction of the tannin, or total phenol from these seeds. The 14% alcohol illustrates a point that may have noticed in red wine pressing. Grape skins from a fresh grape are pretty sloppy and soft. The grape skins from a red wine fermentation are rather firm and hard. And there is this case hardening effect from the higher alcohol. So if you drop a seed into 14% alcohol, you increase the lag, and although eventually the alcohol does increase the extraction rate, as it would be expected to from the lower values, it does initially slow it down. And of course, if we had used something outside the wine range, it might have slowed it even more, and in fact might not have extracted it as fast at the end. It turns out that nearly all phenols are much more soluble in aqueous alcohol than either pure water or pure alcohol. So that one of the best solvents in the world for tannin-like natural phenols is about 50% ethanol or methanol. Well, this indicates then that we could pretty well predict what fraction of the seed tannin was extracted, and I gave you the figure last time that at the times used for making red wine, 3 or 4 days, say, we would have something of the order of 50 to 60% of the tannin, depending on what the net effective alcohol content was over much of that time. Since it would be 0 at first and around 12 at the end, it would probably be safe to say that 50% is a fairly reasonable figure. Now, if we figure that the grapes contain roughly 6 grams or 6,000 milligrams per kilogram, and 2/3 of that occurs in the seeds, then that would mean that there'd be roughly 4,000 milligrams per liter of potential wine that would be in the seeds, and 2,000 that would be in the skins. And these data show that we should expect half of that 4,000 or 2,000 to come out of the seeds. Then if 2,000 should come out of the seeds and 2,000 out of the skins, how does it happen that the typical red wine has only 1,500 or so milligrams per liter? Well, the reason is that the yeast, well, first of all, the grape material itself has a fair amount of protein, and so that a good deal of the tannin, which is a protein reactant after all, will precipitate with the grape protein, and we can illustrate that in other ways. Well, I'll come back to that in just a moment. But also then the yeast cell can be visualized as a bag with a proteinaceous outside. It's a glycoprotein with a good deal of carbohydrate in it, but nevertheless it is a fairly good tannin adsorber. That being so, then you're fining the wine, if you like, with the yeast cells and with the grape protein to remove a good deal of the material. Now, you would tend to remove the larger molecules because they would make the better complexes with the protein. And as a consequence, you'd probably remove a little more of the seed tannin than you would the skin tannin, since by and large, the larger tannins come from the seed. On the other hand, doesn't mean to say that, and this has been a point of contestance between myself and a few other people publishing papers in this area. What they've done is they have made wines in various ways and then said, well, look, the seeds didn't make any contribution, and usually analyzed the wine by adding extra seeds or sometimes removing seeds. We had done a good deal of this before, and we were able to show, at least with white grapes made as if they were red wines, a considerable difference, a tasteable difference of several orders of threshold magnitude in the astringent tannin content if seeds were removed early. So that I am firmly convinced the seeds do make a difference, and the reason they tend to show roughly the same tannin content whether or not seeds are present under their circumstances is that you're going to fine out to about a certain residual level. In other words, the tannin that's left over is going to be about the same whether or not you got some of it from the skins and some of it from the seeds, so that they have tended, I think, to miss the point. And the point being then that there is still some hopes of making a lighter wine by removing the tannin early. Now, this is a summary chart in a different form than the one we showed the other day, and it does bring up the point that these are just round numbers that I've come up with myself. And notice that the red wine we'd say is around 1,500, the pink around a third of that. A richer white wine, particularly sherries, maybe 350. In fact, you'll find sherries and other such wines up to 800, but this might be more typical. White table wine, this may be even a little high, but it's about the top of the usual, and it's about the same as beer, but the distribution in beer is somewhat different, and perhaps, in fact, considerably different than even these figures show, mainly because my analyses of beer don't seem to agree with analyses of beer that other people have reported. For example, the catechin fraction has been reported by other people to be about 100 parts per million, but in our flavonoid analysis, I don't see how that can be true. I don't know where the error lies, but somebody's wrong, possibly us, but at least according to the analysis that we think is, and we've verified it pretty well for white wine, it doesn't show near the catechin content that has been reported in the typical beer, or in beers anyway. I think that's part of the rub. Most of the reports have been on British richer beers, and I was analyzing American beers. Question?
Is there any benefit derived in a white wine from having that much chlorogenic acid or related acid? Or if you took it away, would it suffer in any way?
The major reservoir, other than SO2, of oxidizable materials in wine is phenolic, and in white wine it's mostly chlorogenic acid-like material. Now, the phenolic chlorogenic acid material will react with oxygen but not produce much brown. So in view of that, I think it's a pretty good antioxidant. And I think it's one of the reasons that white grape wines tend to resist spoilage, although we think of them as very delicate. They tend to maintain their identity in the bottle a lot better than white wines made from many other fruits that have less, particularly after amelioration, less chlorogenic acid content. So I don't think you'd taste the difference, but I think it would have a difference in storage survival and general quality retention of the wine.
I was wondering because in that double salting, I could never figure out if the Germans they wanted to check one thing right off the bat. They didn't want to take out the chlorogenic acid.
I see.
I never could figure out why.
Well, I'm sure their reasoning would be similar, and maybe they had shown that, if so, I'm not aware of it being in the literature, that it is bad to remove it completely. The beer people had a similar finding in that, say, under leucoanthocyanins or tannins, they found that if they got it much below the value of, well, they usually say 40 in England, actually, but if they get it too low, then the beer tastes off. It needs a little bit of astringency, maybe a little bit of bitterness contributed by these compounds. and if you use sufficient PVP to bring it to 0, then the beer doesn't taste right. So oftentimes these seem to have a minor, or at least within normal ranges it appears minor, but if you remove them entirely, then they seem to have an effect. One that hasn't been mentioned, I might bring up, well, not much said about it. The tyrosol content is about the same in all these fermented products. It would depend partly on the original tyrosine of the material fermented, but it is present in all fermented products, and it is bitter, and it may have a role of some importance in flavor of some products. Of course, in the beer, there'd be so much bitterness from the hop constituents that the tyrosol bitterness would be pretty incidental as a rule, but perhaps not so in white wine. I said I'd come to one other point in connection with the fining effects of tannin versus grape protein and what survives in the wine. The point I wanted to make there was that if you examine polymeric materials in wines, you'll find that in red wines you cannot find protein. You can find peptides and so on, but you can't find true protein. And the evident reason is, I don't know that it's been proven, but it seems to me one of those things you don't have to prove. The reason is that the tannin content is both high enough percentage-wise and large enough molecules to be an excellent protein precipitant. As a consequence, you don't have protein instability in red wines, but you do have in white wines. Well, that clearly shows that there isn't sufficient tannin to precipitate all the protein in the typical white wine then. That being so, the typical instability in white wine is proteinaceous. The typical instability in red wine would apt to be phenolic, and beer is in between the two, because beer is made by boiling the equivalent of must, the wort, and the boiling process will denature the proteins, and there's a similar, barley and other grains are fairly low in both protein and tannin content, so that they end up precipitating each other pretty completely. So you end up with polypeptides that are not true big undenatured native proteins, and the leucoanthocyanins, which are the small non-tannin type leucoanthocyanins. Then if you get any oxidation of the phenols to make a more polymeric unit, it becomes then equivalent to a tannin. So as soon as you oxidize or otherwise polymerize the residual soluble phenols, then you will be able to precipitate the polypeptides that were in the beer. So as a consequence, the beer instabilities, the chill hazes and so on, are a complex between polypeptide or large polypeptide and small but increasingly growing tannin molecules. And I think the whole picture is we'll come back to this some when we discuss these products in more detail, but I think the whole picture is very informative in this kind of regard. You learn more by studying beer as compared to white wine and red wine than you do about studying just wine or just beer, it seems to me. Maybe not studying, but at least keeping up with the literature as to what other people are doing. Any comments or questions on the grape side, since I know I think practically all the survivors in the course are enology people, so I do want to emphasize this as much as you'd like. That's about all I can tell you about the composition. That, and I would refer you, if you want to get discussion amplification, to pages 41 to 56 in my book with Esau, which tells you up to the time the book was written, everything I knew, and I think pretty much everything that was known about the composition of grapes. We've mentioned a few of these nagging little things, like is it in fact cafeoyl tartrate? Does miracetin appear only in red grapes? Some of these things that have been reported but are not, to my way of thinking, satisfactorily verified. Okay, well, let's go ahead then with the chemistry. Now, this is one place where your textbook is quite good, I think. So we won't spend as much time on this, since we are running a little behind from the schedule. We won't spend quite as much time on this as you might like, to really let it soak in well. But I think, again, if you take what we say in class and any time you can to review both the textbook and these notes, I think you'll find it quite understandable.
Do you have a copy of the notes?
Yes. Now there are several different versions of these notes, and I'll try to, there aren't many corrections, but if you don't have one of the latest copies, for instance, under the references, item 3 says Morrison and Boyd. Well, there is now a third edition published in 1973, so if your copy doesn't say so, you might update it to that. The first question to be raised, I think, is why are phenols acidic? We already said they were. You probably knew it before you started the class. And this comes down to two facts related to this chemistry of benzenoid compounds. And these two facts are that the resonance stabilization of the benzene ring makes it a good deal more stable than the equivalent hexatriene type aliphatic molecule, and then the ionization of the phenol to phenolate contributes additional resonance forms. And the number of resonance forms is related to the stability. The more forms, the more stable the molecule. And that being so, then, the phenolate is more stable than the phenol. And anytime you have that kind of condition, obviously the molecule would rather be in the more stable configuration, and therefore would prefer to be, if we want to put it that way, as a phenolate ion, and this would make the compound want to lose, excuse these anthropomorphic explanations, but make the hydrogen easily removed, and therefore the compound acidic. Now, to run through, you've probably had this done several times in organic chemistry, but we might refresh your memory. If you hydrogenate a single bond in a cyclohexene to give cyclohexane, there's about 28, 29 kilocalories per mole of energy change. The triple bond in the same structure, then, you'd expect to give 3 times as much, so 85.8 kilocalories per mole ought to be the energy change that's produced by hydrogenation. If, however, you hydrogenate benzene, you'll find that the energy change is just about 50 kilocalories per mole, and if you subtract the two, the difference is 36 kilocalories per mole. And by a long series of physical-chemical and organic studies, it's been pretty much verified that the reason for this kind of stabilization is that you have a resonance-type condition, which is written one way, like so. So you have resonance between these two forms, and in fact, as you modern organic chemists know, we shouldn't really write it that way. We should write it this way, which indicates the pi cloud of electrons, and the reason for the extra stability of the resonance forms is that the electrons are delocalized, and you can't say that this bond is a double bond and that bond is a single bond. They both act like 1.5 bonds because the electrons are all smeared around the ring so that no single one of the carbon-to-carbon junctures can be indicated as the one that is more unstable with a high electron concentration, as would be the case if it were a true double bond. And that's the reason for the extra stability. So this idea that the more forms that you can write legitimately, the more stable the molecule is a correct idea, but is a paper modification of the idea of delocalization of the electrons. While we're on the point, this delocalization applies in more ways than one. Why is an anthocyanidin, which is in fact a carbonium ion, a positively charged, well, oxonium, carbonium, depending on where you write the positive charge, but it is the kind of molecule that you'd expect to be highly active, and its red color is because it is the carbonium equivalent of a free radical in the sense of having lost an electron and being a free, unneutralized bonding point. Well, the reason that it's as stable as it is, and it's amazing considering most carbonium ions and oxonium ions that it is this stable, is that it can be smeared out, if you want to put it that way, or delocalized over pretty much the whole structure, the B ring and the A ring, and with the heterocyclic ring included as a conjugated type system. Then the positive charge can in fact be anywhere in the molecule and is concentrated only at a few spots that we'll have occasion to mention later on. But this then gives extra stability. Well, the same thing applies here, and the extra stability in the benzene ring is about 36 kilocalories per mole, and that's quite a bit. Depends on how you define things, but a covalent bond, the carbon-to-carbon covalent bond, is of the order of 50 or 60 kilocalories, so that you have the extra stability equivalent almost to a carbon-carbon bond, and that's quite a bit of chemical strength, if you want to put it that way, or chemical stability. Now, the phenolate ion has, as your notes show, and I won't bother to rewrite for you, some delocalization of the negative ion. In fact, the negative ion, which we'd think of as being on the phenol OH, as we would write the phenolic substance, and if we made the sodium salt of it, we would think of it as like so. But in fact, neglecting that the sodium or whatever anion can be in the solution, we don't have to really worry about it. The charge can be delocalized in various methods and appear in the two ortho positions or the para positions, so that the negative charge can be in fact visualized as in these positions. And of course, since this ring can be visualized as completely free, the electrons are free to be in either resonance form, then you get extra resonance forms as the electron is migrating around along with the normal resonance of the ring. And this extra stability conferred by these extra phenolate forms contributes about 8 kilocalories per mole further. So the phenolate ion is about 8 kilocalories per mole more stable than the benzene ring or the phenol by itself. Therefore, the extra acidity is contributed by the fact that the phenolate is more stable than the phenol, and the hydrogen escapes relatively easily. Now, we can write such structures. Suppose we were just talking about the phenol itself. We can write structures that look something like this, where we keep the hydrogen on and write the charge separation types of resonance hybrids like this, so that we could visualize charge separation that would give extra resonance forms in the normal unionized phenol. But just take a look at what would happen. If you had a positive charge here, then certainly you're going to kick out a hydrogen ion very easily, so that this would tend to lose the hydrogen, and then you'd be back where you were. And not only that, as you probably realize, that charge separation within the same molecule, where you have the minus and plus forms, there's such a great attraction between the two that producing charge separation means that that particular structure is difficult to produce and doesn't make a large contribution to the overall effect of the different kinds that might occur. So again, while we could write some such structure, they can't be terribly important. How acid are phenols, and what influences their acidity? Now, this is a rather important thing, and we won't go into it in any detail from a replication viewpoint, but I hope you understand it quite clearly. Just taking values of pKa's from the literature, and you remember what a pKa is, the way I remember them, if we titrate a weak acid, we get a curve something like this, or a strong acid, we get a curve something like this, and at the 50% ionized form, that pH, the pH at 50% in the ionic and 50% in the non-ionic form would be the pKa. So the pKa is the acidic ionization constant, and the acidic ionization constant is independent of other variables. Well, it has a temperature component and so on, but determined under standard conditions. It is independent of other variables, and therefore you can visualize this as the pH at which the particular species is 50% ionized. Now, if we look at the pK values, well, if we look at the ionization constants and then convert them to the pK values, you have a table in your notes, and you can see that the pK of an alcohol is greater than that of water. pK of water, obviously, is 14. Remember, that's the pH of water is around 14. And the alcohols are higher, 16 to 18, meaning in a water solution, the most acidic thing present, if a water solution of alcohol, the most acidic thing present, if you can call that acidic, would be the water itself. And as a consequence, and you know this, I suppose, if you've done any synthetic organic chemistry, if you want to make the sodium salt of ethyl alcohol, sodium ethylate, and you can do this only in a dry system, because if you try it in water, you'll get sodium hydroxide instead. So that you must make sodium ethylate and such compounds in a water-free system, because the alcohol is less acidic than the water itself. Look at the phenol, on the other hand. It's typically a pK of around 10, and while the difference between 10 and 16 may not impress you very much, if you look at it as a million-fold difference, then I think it surely is impressive. Even in these days of 50 billion annual deficits and one thing and another, I'm still impressed by a million of anything. So that the pK of the phenol would run around 10, meaning then that it would take a pH of 10 to produce it 50% ionized. Now this becomes important in terms of reaction conditions, and while we said the phenol was pretty acidic, to get it 50% in the sodium phenolate form at pH 10, it doesn't sound like it's terribly acidic, because the typical carboxylic acid, the pK would be 3 to 5. So that acetic acid is a great deal more acidic than phenol, say, but nevertheless they're both acidic. An interesting point is that the carbonic acid 2 ionization constants fall pretty much between the two. So if you started to titrate carbon dioxide in solution, the first 50% neutralization point would be at a pH of 6, and the second at 10, a little over 10, which means that sodium bicarbonate then generally will not dissolve a phenol. Sodium bicarbonate would leave the phenol unimpressed. The phenol being more soluble in water in the case of the sodium salt, obviously. Then if you use sodium carbonate or potassium carbonate, you could dissolve the phenol. You'd get the potassium phenolate, and it would be more water soluble. Whereas if you used the potassium bicarbonate or sodium bicarbonate, then you would not dissolve the phenol if the situation is typical and the pK is as illustrated. Now there are other compounds that are at least as acidic or more so, and one that we might just mention for comparison is ascorbic acid. And let me make sure I get this in the right order. Ascorbic acid is a lactone of gulonic acid, and it's an enediol. Now we say in your notes that enols are also acidic, and phenols and enols, as we've said before, have a good deal in common. This material is called ascorbic acid, but its acidity is not because it's the carboxyl function is lactonized, therefore it cannot be acidic from that reason, and it's acidic because of the 2 enol groups, and the pKs are 4.2 and 11.6. Of course, at the 11.6 here, it's alkaline enough, you're going to be breaking open the lactone, so that the first ionization is even more acidic than the typical phenol. So as a consequence, ascorbic acid in your mouth tastes very fresh and nice, acidic, as pleasant as citric or other acids of that kind, maybe more pleasant, but it's because of the enolic ionization. Now this has some bearing in other structures, because phenolic structures, because, for example, if we had a flavonol, without a sugar in the 3 position, this of course is an enolic OH, so that it can be acidic, and not only that, but we could visualize equilibria of this kind, so that we could enolize the situation in another way, and I've lost a bond here somewhere. Well, in any case, we could consider that the hydrogen could be in one place or the other. I guess I'd have to work it around into the, well, let's don't try to work it around right now. In any case, the main point is that in the usual situation, we have an enolic OH, which can contribute to the acidity. The acidity, then, of a given phenol depends on its otherwise present environment, and the environment of the ring, the other substituents on the ring, will influence the acidity. And we have several points to be made in this case. For instance, there are phenols that are called cryptophenolic. You know, a cryptographer studies secret writing. Well, a cryptophenol is a secret phenol, one that doesn't behave normally. An example in your notes here is podotartarin, and you can see that the two phenolic groups are pretty much hidden down inside a pretty sterically inhibited access area. And not only that, but the ortho and para positions are completely covered, so that if you were trying to enolize, or rather trying to get extra resonance stability by moving the electron around the ring, then the localization in the spots that are completely substituted would be a little bit more difficult. And furthermore, if you made the sodium salts, then you'd have trouble. The sodium salt would have a hard time making sufficient polarity to overcome all that insoluble hydrocarbon structure and put the substance into solution. As a consequence, podotartarin won't dissolve in hot concentrated sodium hydroxide. So it has phenolic effect, as can be shown by structure determination and so on, but it doesn't behave as if it were a phenol. On the other hand, some phenols, a notable example being picric acid, are so acidic, they're phenols, they have no other acidic unit, and yet picric acid is about as acidic as hydrochloric, or nearly so. At least it's getting in the range of hydrochloric acid. So there are phenols that, for other reasons we'll come to, are quite acidic. And we've already covered the idea that the sodium ethylate can exist in water, but the second point is that if you have sodium ethylate in the mixture without any water in the presence of a phenol, you're going to get sodium phenolate right quick. And the same thing would be true if you had sodium phenolate and added CO2 to the solution, or a carboxylic acid. So one way to isolate a phenol from a solution, say an aqueous system, where it is not soluble as the phenol but is soluble as the sodium salt, is to bubble carbon dioxide through it. So if you tried to make champagne out of a phenol solution, that the phenol wasn't soluble in the water in the phenolic form, but only in the phenolate form, this would precipitate out and would cause the solution to deposit the crystalline or the amorphous, as the case may be, phenol. This has some bearing, I think, in the fact that sparkling burgundies are generally considered extremely unstable in the gushing sense. And one reason they're extremely unstable in the gushing sense is that you are throwing any possible phenol out of solution. Of course, the low pH of typical wine would tend to do that anyway. And then these crystalline or deposited sections of pigment and tannin would form as a nucleus for the CO2 to generate, and you'd get gushing from the CO2 coming out of the sparkling burgundy, and you wouldn't have a similar problem with ordinary white champagne. The inductive effect can be visualized as sort of a magnetic type effect. If you have some group that withdraws electrons, attracts the electrons to itself, so that the oxygen becomes less electron rich, then the hydrogen ion can escape more readily. So if we had a phenol, and whether or not it's acidic governs. If it's acidic, the hydrogen escapes very readily. Then if we can make the oxygen less electron rich, then it's going to be easier for the positive hydrogen to escape. So anything that would draw electrons away from the oxygen would make it easier for the hydrogen to escape and make it more acidic. So this would be the inductive effect, and vice versa. The inductive effect of something that supplied electrons to the ring would make the oxygen more negative, and therefore the phenolate would be harder to form. And on page 4 of your notes, we have a list of some properties of simple phenols, and if we just look at the top where there's ortho, meta, and parachlorophenol, you'll notice that the pKa's decrease from 8.13 for the orthochloro to 8.8 for the meta and 9.2 for the para. So that we have here the inductive effect in the sense that, and if you compare it with plain phenol is less acidic than the orthochlorophenol, so the chlorine is withdrawing electrons, has an inductive effect to make the phenol more acidic. And the nearer the inductive effect is to the site, since you can visualize it as kind of a magnetic type attraction, the nearer it is, the more effect it has. So if we put the chlorine in the ortho position, it increases the acidity more than if we put it in the meta, and more yet than if we put it in the para position. So in inductive effects, the nearness to the atom being the local part of the molecule being affected, the more the effect. The second group of effects would be extra resonance contributed by what I would call double bond character effects, and this is best illustrated by the nitro group as shown in your notes. And picric acid is the phenol with the 3 nitro groups. So we have maximum contribution of the extra resonance forms. Each nitro group in these positions can contribute, and so you have so much increase in acidity that this becomes like a mineral acid in its very high acidity. Part of the reason they contribute extra resonance forms is that you can have structures that involve the delocalization of the negative charge in structures such as this, with the nitrogen appearing positive, and then the true electron from the phenolate ion and the other charge separation type electron being drawn in this fashion. We can get the same kind of structures with the carboxyl group, and the carboxyl group would ordinarily increase the acidity of the OH group, but there are other effects that can influence this. For instance, and on the top of page 3, we mentioned that the localization of the carboxyl. Now remember, when we're talking about acidity of the phenol, we're talking about the phenol itself. The carboxyl in the same molecule, of course, is more acidic. So if we ionize the carboxyl first and then ionize the phenolate, you would expect by the extra resonance forms available that you would increase the acidity of the phenol. But it depends on where the carboxyl is located. If it's in the para position, it does increase the acidity, but in the ortho position it does not, because in the ortho position, in the case of the carboxyl at least, we have a situation where, and we can draw this in more than one way, but the hydrogen is bound, the hydrogen bond occurs between the carbonyl and the phenolate, which tends to keep the hydrogen of the phenol from escaping. So salicylic acid is, the carboxyl decreases the acidity of the OH group, whereas in parahydroxybenzoic acid, the phenol is increased in acidity. Well, yes, question? Well, you would think it might, and the only reason I can say as to why it apparently doesn't is you would ordinarily need, to make a hydrogen bond, you would need a concentration of electrons beyond just a simple spare electron. In other words, here we've got the equivalent of the double bond electrons besides the unpaired electrons, so you in a sense have a greater concentration of electrons. Not only that, but we're visualizing here a local positive which dilutes the effect of this negative to some degree. So you would think that might be so, and I think it's possible perhaps to show that ortho nitro has less effect than a para, but the difference is small in that case, not nearly so large as it, and they're not really opposite. In both cases it enhances the acidity, but it enhances it less in the case of the ortho compared to the para. Well, unfortunately, I'll have to pick up from here again then.